Well, I said to you at the beginning, this is going to be very dry today, and I know you tell me all my lectures are dry, but this is dry. I need to go through a description of friction clutches with you. I'm going to take you through the theory, rather like we showed the theory of belt drives, where we built it up from an elemental strip of belt, if you remember. We're going to do a very similar thing here. We're going to build up the theory from an elemental strip on the surface of a clutch plate. So I'm going to show you that, and eventually it will evolve into two types of theory, and the syllabus wants you to be aware of the two types of theory. So you don't have to worry too much about understanding the detailed breakdown I'm going to show you. I think at your level of study we should have an idea of where the equations are generated from, but ultimately it will be a question of you choosing appropriate equations, rearranging appropriate equations to solve the problem given. All right, but it will be for the first probably 20 minutes a little bit laboured this, so try not to fall asleep if you can help it out there. We will get into some questions, then you'll start to see how the equations are used and so on. This is quite analogous to belt drives in the way we approach it. Theory applied, and then we'll do questions on the on friction clutches in this case. So what you're looking at on the screen is what you should be seeing in your book. It's page 29, and I'm going to flick through. You'll find some gaps in the pages. You've got some sort of text is missing, and I'll fill in the gaps for you as I read through the notes. I'm basically going to browse the notes, highlighting certain things as we go through. Okay, so what you're seeing on here are two diagrams on the screen. On the left-hand side, you're seeing a single clutch plate, what we've got over here, a pair of plates there. And over here on the right-hand side, we've actually got two pairs of friction surfaces. We'll talk more about this later on. We're going to have a contact on this surface and also a contact on this surface, so it's called a two pair there of friction surfaces, and we'll talk about the number of friction pairs later on, because that comes into the torque calculations we'll be looking at. So that's just diagrams shown there. Okay, so here's the first slide. This will be on the next page of your notes. You'll see there's some gaps in the notes. If you want to just add these words in, I'm just going to read through some of the notes just to outline some of the background to friction clutch and so on. So figure 1, shown on the screen there, illustrates a simple disc clutch. It's got one driving and one driven disc shown, okay? So the principal operation is totally dependent on the friction involved, the driving friction involved, and that's created by the two clutch discs that we're looking at. They're forced together, depends on different mechanisms of forcing them together, but that axial force that they're joined together, we will be looking at later on how we derive that force, how we calculate that axial force. That's an important characteristic of the friction clutch configuration. So we're going to be applying a pressure to the discs by either mechanical or hydraulic means. We're not really too bothered with that. We will sometimes get involved with spring stiffnesses because that's part of mechanical application later on, but basically the force is applied, the pressure is applied via either of those means. As with other components around friction, they're designed to operate both dry and wet. You'll see in the calculations later on we will have wet configurations and dry configurations. Basically that boils down to different friction coefficients as far as we're concerned, but we need to highlight the different configurations between a wet clutch and a dry clutch. Okay, the oil that's used in the wet clutch effectively increases the cooling effects, so effective cooling medium for any heat that's generated. But what we find when we've got a wet clutch configuration, we have to use multiple discs to generate the friction required, because in a wet clutch configuration the coefficient of friction drops right down. It's really quite low. Again, you'll see this a bit later on. So we need to have multiple clutch plates in a wet configuration, more than we would need in the equivalent dry configuration. So in a multi-disc clutch, the driving discs rotate with the input shaft. The clutch is engaged using, as we said, hydraulic pressure or mechanical pressure, and that's generated from the master cylinder using the clutch pedal in a car. And the driving disc is just a configuration of the manufacturer. Driving discs are constrained by keys and keyways to rotate with the input shaft. Just background information there, really. So on engagement of the rotating drive discs, they're forced together and from that we provide a torque to the output. And the forces and the torques are the things we're particularly interested in. We're going to calculate the force and the torques involved here. When the clutch is disengaged by releasing the hydraulic pressure or through spring action, the discs are free to slide axially, and so they separate themselves. On figure 2 on the previous slide, it shows driving discs including what's termed backing plates, which only provide one friction surface, whereas the middle driving discs on that figure provide two driven surfaces, so there's two contact surfaces. We've actually got 5 discs and they produce 4 driving and 4 driven contact surfaces, and we term that 4 pairs of friction surfaces. I've got a bigger diagram I think here I can show you. So what they're trying to say here, a contact surface here, so contact surface here and here, and the contact surface there. Alright, so those are like drive and driven surfaces. So we've got 4 pairs of contact surfaces there. And of course, the more pairs of contact surfaces you have, the more torque you can generate. And we'll be looking at this later on. It doesn't really affect our calculations greatly having 3 or 4 or 5 pairs. We just really factor up the torque from one pair of contact surfaces. But as like belt drives, we have multiple belt drives. We work out the power generated by one belt drive and then factor it by however many belt drives we have. And the same really applies to friction pairs of surfaces. But nevertheless, we need to be aware of the contact surfaces. It's not always easy to see the arrangement of them, but that's those red lines I'm trying to show you. They're the 4 pairs of contact surfaces in that particular configuration. It's not too clear to see. This is not in your notes, but this is just showing you again. This is a friction clutch here. We've got 2 pairs of friction surfaces. Here, there's a contact surface here, and there's a contact surface here. So that's classified as 2 pairs of friction surfaces. Looking at permissible pressure on friction surfaces, it ranges, as it shows there, from 0.35 megapascals to 2.8 megapascals, and you'll see later on pressure is a very important characteristic of a friction clutch. But these pressures depend on the materials involved, the clutch environment involved, and severity of operation. If you've got dealing with things like cone clutches, for example, sometimes they're really rugged environments they're used in, so pressures have to be determined on the environment they're sometimes used in. The friction coefficient, symbol mu in most cases, for dry operations range from 0.2 coefficient to 0.27-ish. And you'll see in a moment it's much, much lower when you've got wet configuration. So 0.2, 0.27, normally 0.3 for dry friction clutches, friction coefficient. But when we have oil immersed clutches, which we do have sometimes, they're normally used for heavy duty, where there's lots of heat to be removed. So when the clutch is located, say in the gearbox, cannot always easily be isolated from the oil, so it has to run wet. But obviously the friction coefficient is much lower than when it's a dry consideration. So we have to have larger axial forces employed. You employ larger forces to push the plates together, so that increases the friction. We find that oil clutches are smooth working and they have fairly low wear rates. That's a benefit of them. But here you can see what oil immersed clutches, their friction coefficient is very low, 0.04 to 0.1, so that's very low. So you see we need a lot more force generated to try and increase the friction, or we need multiple plates to try and effectively increase the friction effects. So when we're designing wet clutches, we've got those other considerations to take into account. This is just background to the topic area here. Okay, assumptions. Lots of assumptions made in friction clutch theory, as there were in friction drive theory, of course, friction belt drive theory. And one of the assumptions made, it's a reasonable assumption to make this, is to assume that the wear rate is uniform or constant across the clutch plate rubbing surfaces. It's an assumption, but it's one that's sometimes made in the design of clutches. It's also assumed that the torque is equally shared by all the clutch discs, and also that the friction coefficient remains constant across the entire operation, the entire clutch face here. And the last assumption is considered to be a rather unrealistic in most textbooks. It makes the analysis easier because you've got varying friction coefficient, and that really does complicate the analysis. You'll see the analysis is quite complicated anyway. You complicate it still further if you have varying friction coefficient across the surface. So we often assume it's constant friction coefficient, but that does put errors, it does put assumptions into the calculations. It's slightly unrealistic. So often you design clutches to be a bit more sturdy, a bit more sort of heavily designed than perhaps they would require for the service requirements because of the assumptions we make in the analysis of the clutch plate, clutch design here. As it says there, in practice, engineers' tendency to design a new clutch, over-engineer a new clutch to allow it to bed in. And once it's bedded in, hopefully it then has the characteristics that are required in the specification. After the initial bedding in process, the wear then tends to be uniform across the surface, and the friction coefficient able to meet the clutch design specification. So, as I said, they're over-engineered when you first design a clutch, but hopefully when they bed in, you've got their design right, so they then account for the conditions you need and they perform satisfactory. This little diagram on the right-hand side is showing that the pressure times the radius, which is considered to be the analysis of the wear, is constant. The wear is assumed constant across the surface, and the pressure distribution based on that assumption will change from being highest pressure at the inner surface of the clutch plate, as is sort of shown here, to the smaller pressure at the outer surface of the clutch plate. So at the inner radius you have the highest pressure, and at the outer radius you assume you have the lowest pressure. But that relates to what's called a constant wear effect, a constant wear assumption. It's often used when designing clutches. They're quite complicated bits of kit to design. We'll come across that again later on in the work we're going to look at. The analysis. So this is quite dry, but I'm going to try and build it up slowly for you. And then we'll get into where the equations are. So just bear with us another 10 minutes or so while we just outline this, and then we'll get more into the practical side of things and application of this. So this is the analysis of flat plate clutches. We're going to go through an analysis here, and then we're going to diverge using two different assumptions. The syllabus talks about constant wear and constant pressure assumptions. So we're going to derive our equations to the stage where we can then make those assumptions. You'll see we'll end up with two different types of formula relating to the different assumptions made. So in the figure, this is all in your notes, two surfaces are pressed together. So these two surfaces are pressed together with an axial force. They've called it W. So W is the normal force applied to the two surfaces here. We have an outer and an inner radius labelled as R0 for the outer radius, that's shown over here, and Ri for the inner radius shown here. The pressure is at the various radiuses. We're looking at R is at the is P across the disc we're looking at here, and later on we'll talk about constant pressure and varying pressure. So what I'm going to try and do is build up the analysis, because I think it's interesting just to see how the analysis developed. It does bring in lots of your math work from level 4, level 5 here. So to see how it's applied here, you don't need to worry too much about this. You're not going to be asked to do this, but just to show how things are built up here. What they do, as we did with the belt drive, is they consider a very thin piece of the, in this case the ring. We considered a very small segment of belt in our belt drive analysis, and we looked at all the forces acting to the left and the right of the belt. Here they consider a very thin annular ring, and that annular ring is here. If I try and show you here, that's the annular ring. Just a bit of annular ring here they're talking about. Now that's very, very thin. The thickness of it, you can see they've labelled as dr, and that dr means it's really thin, very, very, almost difficult to measure the thickness of that strip there. So if you wanted to work out the force applied, so we've got a pressure applied over the entire surface, but we're just talking about the pressure applied over that little strip there. This would be the pressure. And to work out the area of a very, very thin strip, you can actually use the formula pi dt in some textbooks, or 2 pi r multiplied by thickness. So using notation here, we've got 2 pi r, that's basically circumference of that red strip. And if we multiply it by the thickness, which is very, very thin, the thickness is dr in the sketch shown above. So multiplying 2 pi r dr gives us the area of that very thin strip, and if we multiply that by the pressure across the strip, we will get the force applied. So it's force equals pressure times area, and the force in this case is the dW. Now if we integrate across the entire profile from the inner radius to the outer radius, it's back to integration process here, we're integrating and taking the constant 2 pi outside the integral. So we've got 2 pi integral of p multiplied by r, pressure times the radius, with respect to r, because we're integrating with respect to the radius here between our limits. We can work out what the total force W is applied across that surface. So that's what equation 1 has done for us. It's given us an integral that we can use to work out the total force applied, assuming a pressure across the profile of the disc we're reviewing there. Now we also need to work out the frictional force. Now I don't know if you remember this is back to level 3 mechanics, but frictional force is the coefficient of friction mu multiplied by the normal force. And this was our frictional model here, where n is the normal force, the force at right angles to the surface we're considering, the frictional surface we're considering, and then the frictional force was parallel to the frictional surface we're considering. So looking at our disk here, our W force, or the dW if you like, is the force that's a normal force. It's normal to the direction of the clutch plate here. And when we work out our frictional force, we're actually working out the friction on the disc, on the surface of the disc of the strip dr there we're looking at. So the friction force, using our formula mu n, would be mu multiplied by, for the strip, the dW. The dW is the normal force on that little strip. And we know from above that that would be mu multiplied by dW, and dW is the 2 pi PR dr. That's this bit up here. That's the dW, just applied it here. So we've got an equation here for the friction force on the ring at that particular location. So from that, we can work out the torque on that ring. So what we're effectively doing here is having a frictional force. So I just sort of draw it over here on the ring. There's a frictional force. I'll show it. Let's put an angle. It doesn't matter where I show it there if you like. There's a frictional force applied here, which is our FF. And that multiplied by the radius from the center of rotation will give us a torque. So that frictional force that on that elemental strip, FF, effectively there, multiplied by the radius of that strip, which is this radius shown here, will give us the torque from the elemental strip. And that's all I've got here. It looks complicated, but that force is from the previous slide, the mu multiplied by the n, the 2 pi PR dr, and I'm multiplying that by the radius. The strip is at radius r in this case. So I can end up with the moment of the frictional force about the axis, in other words the torque of the elemental strip about the axis, as shown here in terms of the 2 pi mu PR squared multiplied by dr. So very slowly building up the formula for the elemental strip. If we want to find the total torque applied across the whole disc, and we've got to integrate then. So in this case, we'll be integrating the PR, because the pressure and the radius is varying, and we're at the moment assuming the pressure can vary. So PR squared, which is this term here, is a variable, so that's inside the integral, which we integrate with respect to dr there, and outside the integral they've taken the constants, which would be the 2, the pi, and the coefficient of friction, as we said earlier, is assumed to be constant across the entire surface. So another integral here, but this integral, equation 2, is for the torque applied from the frictional surfaces. So we're integrating between the inner radius and the outer radius. So this is the point at which we can start making assumptions here. We've got two equations. On the previous slide, we had equation 1. Slide here, equation 1. This relates to the axial force. There's an integral of PR, respect to r, between our limits. And then we've got this equation here for the torque, which is integral of the PR squared, respect to r, between our limits. Okay, what we're going to do now is make some assumptions. The syllabus wants you to be aware of the assumptions. So equations 1 and 2 can be integrated with the assumptions relating to variation in pressure with radius. So the following theory outlines specific assumptions, generates associated equations, and then from these equations, from the final equations we get, we can design our clutches based on these assumptions. So, two types of assumptions. The first one is looking at unworn clutches. Okay, so for an unworn clutch, the pressure is assumed constant across the entire surface. So, in other words, the P in the previous integrals, for equations 1 and 2, can actually come outside the integral because we're going to make that assumption that the pressure remains constant across the entire clutch surface. So, notice the P is outside. So, there's our integral. Equation 1, the P was inside here, but for an unworn clutch, we're going to take the P outside the integral sign. So we're simply integrating R with respect to R between our limits. If you go back to integration, that's a very straightforward integration. That's integrating x with respect to x. That becomes x to the 2 upon 2. For an integral tables, that becomes R to the 2 upon 2 using the notation in this question. So equation 4 labelled here, we've got the 2 pi p, p is constant, and then we've got r squared divided by 2, so our function now, and we've got the limits of r0 outer radius, ri inner radius. And all I've done is put those into the equation to get equation 5. And this is one of the first equations you want to now note. This is going to be a useful equation for an unworn clutch. If you want to work out the total force that's required, then we can do that now from the formula pi multiplied by the pressure, which is constant, and then multiplied by the outside radius squared minus the inside radius squared. So first formula there we're going to be using later on. Continue with my unworn clutches here. What we've done now is rearrange this equation. Equation 5 is being rearranged in terms of pi and p, because pi and p is actually a constant in this particular case. Pressure is constant, so pi is obviously constant. We're going to rearrange the equation because in a minute we're going to put the equation 6 into another equation that we use for torque, so we get torque related to axial force. So just bear with me with equation 6. I've just slightly rearranged it, in other words divided both sides by the bracketed term, and we'll use that in a moment. Now look at the torque. So we've looked at the force applied. W is the force applied, pushing the two friction plates together. Now we're going to look at the total torque that can be generated for an unworn clutch. So again, the P is outside of the integral because it's constant. So inside the integral, we're just integrating the R squared with respect to R. But again, R squared is a standard function like x squared. Integrate x squared with respect to x, we get x to the 3 upon 3. Integrate R squared with respect to dr, we get the r cubed upon 3. So standard integral, you could integrate this if you wanted to, standard form. Okay, all I've done on the next slide is impose the upper and lower limits. So equation 9 here has the limits imposed. What I'm going to do now though is impose the equation 6 above, the one we rearranged in terms of pi p. So we're going to put the pi p here in for the pi p here. So we're going to replace the pi p with a w divided by the r0 squared minus the ri squared. So that's what we've got here. That bit there is basically the equation 6 being inserted. And that gives us equation 10. Now we've got a nice equation you'll see later on. If I want you to work out the torque that can be generated for a clutch, assuming the constant pressure, it's an unworn clutch, we've got an equation that links nicely to the axial force applied. Equation 10, we can use that equation. Okay, so we've got the value of mu, and we've got our geometry with our r's and so on. We'll be able to work out the value of w from our previous equation, and we can find the torque that can be applied. Now, as I said, if you want multiple clutch plates, you simply just factor up the torque equation by the number of friction pairs of surfaces. And again, we'll highlight this later on when we come to look at examples. So between equation 10 and 11, it's just that n term that's involved there. So very analogous to belt drives. You want to factor up, so you've got 3 V belts in the system. You work out the torque applied, torque generated by 1, and factor it by 3 for 3 belts. We do the same kind of thing with friction pairs on our clutches. We're now going to look at what's called worn clutches. Now, in a worn clutch, we assume the wear is going to be constant across the surface, not the pressure. So it's a different assumption made here. And what it boils down to, basically, we're looking at where is related to velocity, and linear velocity, if you remember what we discussed in the previous sessions, linear velocity relates to the radius. The further out you are from the center, the bigger the linear velocity. The angular velocity remains constant, but the linear velocity increases. So where is basically related to velocity, and velocity is related to the radius. So it can be stated that the pressure times the radius effectively relates to the wear of a surface, and we call that a constant C because it's constant wear assumption, uniform wear across the surface. So in the equation we're going to generate in a moment, you'll see that P and R now are variables because the pressure is not constant, so it can vary across the surface, and of course the R is a variable as well. But P multiplied by R must equal to a constant C. So pressure times radius is equal to some kind of constant. We're saying the wear is constant across the surface. So that's the next assumption made. This is classified as worn clutch theory. So now what we're going to do is take the P outside the integral sign along with the R, because P and R are considered to be a constant. So P and R comes outside. So that C there we've got there is actually P and R. That's a constant. So inside the integral now we simply got the dr, or if you prefer 1 dr. It's nice to see the 1, there's a 1 there. A 1 dr. So the integral is even easier this time. Integrating 1 with respect to R, we get R. And that's what's shown here. Again, don't worry too much about the derivations. You're not going to ask to be shown the derivations, but you do need to understand the backdrop to the theory, that's all. And again, imposing my outer radius and my inner radius into this equation, we get the axial force related to a worn clutch, when we're assuming that the constant wear is applicable, is 2 pi c. C is the P times R, and then multiplied by the, in brackets, the outer radius minus the inner radius. So there's an equation for axial force for a worn clutch plate. And we're going to generate the torque for a worn clutch plate. And again, we can do the same kind of approach here. So what I've done here, just a bit of rearrangement from the previous slide. I've just taken my equation on the previous slide, equation 14, and I've rearranged it in terms of pi c, because pi c are constants here. So dividing by 2, dividing by the bracket, I get the pi c is equal to W upon 2 multiplied by R0 minus Ri in the brackets. We're going to use that in a moment when we generate our torque equation. But going to the torque equation, back to equation 2 we generated. In this case, we're going to take the pressure and the radius outside, because P multiplied by R is assumed a constant. So all we get left with inside the integral now, taking P and R outside, is an R inside the integral, because P and R has gone outside. That's the constant C there. And again, we've got a nice standard integral to integrate. Integrating R with respect to R, that becomes R squared upon 2. Just put my limits in for equation 18, put the upper and lower into the equation. Okay, so our final slide here, what we're going to do now is put the equation 15, this equation here for pi c, we're going to put that into the, I'll go back to my colours here, so the pi c here is going to go in here, pi c, so we'll bring in the W upon the 2 multiplied by the bracket, and that's what's happened here. The W divided by the 2 multiplied by the bracket there is put into the equation. Okay, so that's just again trying to get W into the equation. We want our T's in terms of the actual force. And you can see there that there's some cancelling going on here. You can actually cancel the R0, this term on here, with the squares on the top line. Actually cancels off. I haven't showed you the individual calculations here, but you can actually cancel off with a square on the top line. It should really show that, but it's not shown there. And that simplifies to this equation here. So equation 20 here is torque now is a half of mu W multiplied by the R0 plus the Ri, and that's now the torque that can be generated from a single pair of friction surfaces for a worn clutch. And again, if we want to have multiple pairs of friction clutches, we can multiply that by n. So it's another equation. Okay. So now what we've done is generate our equations for an unworn clutch analysis or assumption and a worn clutch analysis. And I'm just really following through what's in your notes here. Just looking back at this ideal of the PR is equal to constant, the constant wear, which is the prevalent theory, I must say, of the two theories. The constant wear theory is assumed that the pressure times the radius is always a constant. So as I said before, what you find here is that the pressure is largest at the inside radius. That's where the highest pressure will be, where the radius is smallest, and it will be the lowest pressure at the outside radius. The radius is bigger there because P multiplied by R has to be a constant across the surface. So at the inside surface we have a small radius, large pressure to give us a constant. At the outside surface we have a large radius, small pressure to give us the same constant. Okay, so the maximum pressure in this theory is assumed to occur at the inside surface. And again, this is just some sort of design information, just for really reference here. Clutch plates are often designed with a specific ratio between the inner and outer radii. Because this maximizes the torque transmitted. So if you're in the field of designing clutches, this kind of ratio is sort of an optimum. The RI radius is 0.58 of the R0 radius. And also the torque transmissible by a worn clutch is less than that of an unworn clutch. So unless you're told otherwise, you always use the worn clutch theory when you're designing a clutch. But some of the questions we'll look at unworn clutches because that's sort of the best condition you can get. So this is just design characteristics of clutches. And this slide just shows you some other formula we'll be using as the topic proceeds, not necessarily all this week. We will be using the power equation. Power is torque times angular velocity. We'll be able to work out our torques from our frictional clutches from calculations using the formula on the previous slide. And if we've got the angular velocity, we can find the power. So we'll be using that one. And probably not this week, but soon we'll be using the spring stiffness equation. We'll talk about that more when we get there. But spring stiffness is a characteristic of a spring. You normally look it up in a catalogue or on the internet. And it's the force applied to the spring divided by the extension or the contraction of the spring. Gives what's called the spring stiffness. We'll look at that later on. That's something we'll look at when we come to use these spring stiffnesses. So we'll look at that later on when we come to the questions. Okay, I'm going to take you through some examples where we're going to use the formula. It's basically the formula you have to be familiar with, all right? Not so much the derivation, but the derivation is sort of useful to the background of what we've got here. So example 1, this will be in your notes. Let's read through the question. Let's extract the information of the question, and we'll go through on the board the equations required. So we've got a flat plate clutch. We will look at something called cone clutches later on. That's in future weeks, but flat plate clutches at the moment. And it's designed to have 4 pairs of friction surfaces, 4 friction pairs. We're told that it rotates at 240 revs per minute, and it has a friction coefficient of 0.26. So we'll extract all this information in a moment. The axial thrust that's applied at forcing these friction surfaces together is 400 newtons. That's a W. And we're told that from geometry we've got a maximum diameter of the material of the surface is 250 millimeters, and the minimum diameter is 160 millimeters. They want us to simply work out the power that can be generated, power that can be transmitted, if you like, in A, when the clutch is new, so that's an unworn clutch, and B, when the clutch is worn. Okay, so we're just really going to use the appropriate equations that have been derived to work out first of all, the torque, and then the power. So let's get the information from the question first of all. That's the first thing to do here. Okay, I think that's all the information out of the question. So now we go straight for the equation. So the first thing I want to do is to work out the power that can be generated for a new clutch. So that's our first configuration. So part A is to be classified as an unworn clutch. In this case, the pressure is assumed constant here. So the first thing we're going to do is work out the torque. So part 1, if you like, find the torque. And of course what we have to do is work out the power. So it's just torque times the angular velocity to find the power. And then part B, we do it all again basically, but now we're using the worn clutch theory. So again, go work out the torque. Again, if I could let you put the numbers in, I appreciate it. It takes me a long time to write it down here. So putting the numbers in, I get 42.64 Newton meters. There's my actual work solution. So that's my value for the torque generated for the worn clutch theory, which is the constant wear theory, if you like. And then, of course, the power, same formula again for power. Okay, so you can see very similar power outputs from the two theories in this particular case. So example 2 then. A multi-plate clutch requires to be able to transmit a torque of 160 Newton meters. So we've got the torque this time, so we've got the T, so they're looking for something else. But so the external and internal diameters of the friction plates are given as 100 millimeters and 60 millimeters, respectively. If the friction coefficient between the rubbing surfaces is 0.25 and the maximum pressure is 1.2 newtons per millimeter squared, we've got to calculate the minimum number of friction face pairs here. There's a number of pairs of friction surfaces and the axial clamping force. We've got to use both unworn and worn clutch theory and state assumptions made. Okay, so a bit of work. Let's get the information from the question as always. Let's forget about the analysis for a second. So we've got a torque given this time. So torque, that's given as 160 Newton meters. We've got the diameters again, the external, I can just write them down. So external diameter, internal diameter. So, and again, we will need the radii for those. So let's go and work that out now. So we need to get the diameters in terms of meters, and then it's the radius we really want. So just lay it down. What else are we given? Or friction coefficient. So friction 0.25. It's dimensionless. And we've got the maximum pressure as well, so we need that. So P max, I'll call it. And that's 1.2. Well, that's in newtons per millimeter squared, so we need to be careful of that. That's sneaky. So 1.2 newtons per millimeter squared. Not sure if you are familiar with the conversion, but basically that's the same as, again, it's in your booklets in the conversion section, this one. It's actually the same as 1.2 meganewtons per meter squared. So, okay, so 1.2 newtons per millimeter squared is the same as 1.2 meganewtons per meter squared. Mega's 10 to the 6 newtons squared, so be careful there. Anything else we need? I think that's it, isn't it? We've got to find the number of friction pairs, and we've got to find the actual clamping force required, it says there. We've got to use both theories as well, haven't we? Unworn, unworn. So let's consider the unworn theory first then. Okay. Using, okay. Now looking at the information given here, so we've got the torque here. So we can, so look what we're going to find here. We've got the T in this particular question. We need the W, don't we? But we can find the W. The transposition I can see coming up here in what we're going to do. So let's work out for the unworn clutch. Let's work out what the W is going to be. This is back to the equation we derived on the previous slide. So looking at the unworn theory, you should find this equation, W is equal to, so unworn clutch theory assumes constant pressure. So P was given to us here, the 1.2, assuming that's going to be constant then. And we've got our geometry given in the question. We can find the W. So that's multiplied by the 1.2 multiplied by 10 to the 6, because we've got to use the newtons per meter squared. And then that's multiplied by the outside radius squared minus the inside radius. Hopefully you get 6032-ish. That's newtons, of course. That's an actual force. And what I'm going to do now, I don't know if you can see your way through this, but what I'm going to do, because I'm given the torque applied, I can use the torque equation. I've got the W, and I think I'm going to rearrange that to find the number of friction pairs required to meet this configuration, this specification. So that's where I think I'm going to go next. So a little bit of transposition coming up So I'll transpose, personally I'll transpose algebraically at this level, see if we can transpose. You've got to make n the subject. That's what you're after here. How do you make n the subject of the equation? Okay, it's actually quite straightforward, this one, to transpose, to be honest. I don't know if you've had a little go at it. But you want to make n the subject, so you've got to remove on the top line the 2 mu w and the bracket, all multiplied together. So I can simply divide by 2 mu w and the bracket all at once. And then I multiply throughout by these 3 and the bracket on the bottom line. So it's not quite as difficult as perhaps it first looks to transpose for n. So n is equal to, and that then gives us the value of n. I'll let you put the figures in and see what you get for your value of n. And my value of n was 2.6. So 2.6 clutch plates, which of course we can't actually have, but that's what the calculation would be saying. So we'd have to use n is equal to 3. We can't have 2.6 pairs of clutch plates. So because we've got more pairs than we theoretically need to use, it actually means that the force applied can actually be lower, because the question did state what is the actual axial force applied. We know theoretically it needs 6,032, and that 6,032 has helped generate the 2.6 pairs. But we're going to have to use 3 because obviously we can't use 2.6. So we actually need slightly less force applied if we're going to use 3 pairs. And we can just proportion that using the 2.6 to 3 ratio. So the actual axial call it W dash if you like, will be the 2.6 divided by 3 multiplied by the 6,032. So we're kind of factoring down that value, because the 6,032 effectively gave us the 2.6 clutch plates, but we're going to use 3 from a practical consideration, so we can then factor down what the actual axial force we need. So I work it out to be 5,228 newtons. So with our design of 3 friction clutch plates, that would be the actual force we need, slightly less than the theoretical value calculated above. And of course that can then be translated to the pressure. If we don't need as much force, then actually we don't need quite as much pressure. So we can do exactly the same approach here to find the actual pressure required. So the actual pressure, I call that P dash. Again, that will be the ratio of the clutch plates, 2.6 divided by 3, but this time it's multiplied by the pressure that was given in the question. I think it's 1.2 megapascals. So my value is 1.04 times 10 to the 6, if you want it in newtons per meter squared, or pascals it's sometimes written as in pressure terms. And of course that's the same as, that's equivalent to 1.04 newtons per millimeter squared. So back to the original units given in the specification, if you like. Okay, so that's the actual force required and the actual pressure required in this particular case. First part of solve using the unworn clutch theory. Do you want to have a go with using the worn clutch theory? It's the same approach, it's just a different equation. So you need the equation for the axial force for the worn clutch. You need a torque equation for the worn clutch. So don't forget the underpinning theory here, the underpinning assumptions for the worn clutch theory. We assume that the wear is constant across the entire surface, and the wear is deemed to be proportional to the pressure times the radius. So we know that for that to be true, to have the same value of C across the entire surface from inner to outer radius, then the maximum pressure must occur at the inner radius. And they've given us the maximum pressure effectively in the question. So we can work out the C here. It will be the 1.2 multiplied by the 10 to the 6, and that's multiplied by the inner radius, 0.03. So in the unworn clutch theory, it's pressure constant in the worn clutch theory, it's wear is constant, and wear is defined as pressure times radius. So now I've got my C value, I've got my geometry, I can find W. What do I get from my W? Now we can use the torque equation to find the number of pairs of friction surfaces. Don't forget we're using the torque equation for the worn clutch theory. So again, you need to transpose it. Have a little go at transposition. Rearrange it for n, see what you get. Again, they look nasty equations, but actually quite reasonable to transpose here, to be honest. To my calculations, I get 3.54 pairs of friction surfaces each time. So we'll be looking at 4 pairs then. And again, we can work out what the actual axial force will be, which is what the question actually wants us to find, by factoring the original force, W, by the ratio of 3.54 upon 4. According to me, I get 4,000 for that. Call that a day there. So what we'll do next week is we'll pick up on this. We'll briefly recap what we've done this week, and then we'll do some more questions and perhaps bring in some more practical considerations, start looking at spring stiffness maybe come into play there, get more familiar with the equations.